Yeah, we can start. Can I start now?
Give an introduction and start.
Good afternoon to all of you. First of all, thank you each and everyone for being here with us today. We are pleased to welcome all of you to this technical talk on electrical vehicle trends and research. So first we shall begin the session with a silent prayer. So I request all of you to please rise up. Thank you all. Please be seated. Next, I invite Assistant Professor Rini Varghese, Department of EEE MBITS, to deliver the welcome speech.
A very good afternoon to one and all present here. In fact, I'm privileged to welcome Dr. SHIMI, my own teacher, before you, my dear colleagues and my dear students. A beautiful relationship started from 2003 when I was in semester 3. I remember those days when she taught me network analysis and synthesis in semester 3. And from those days to this very moment, we are sharing a very beautiful relationship. And I just thought of sharing her experience and her knowledge with you, dear students, and with my colleagues. So so that you can explore the world of electric vehicles. So when I contacted her for the same, without any delay, without any second thought, she accepted my invitation for delivering the session. So in fact, I am privileged and I am in very pleasure to welcome my dear teacher, Dr. SHIMI for the session. Okay. And again, I invite our HOD, my colleagues and my dear students to attend the session. Thank you.
Thank you, Rini, for this introduction. And so now let me just share my screen.
Thank you, ma'am. Today, the resource person for this session is Dr. SHIMI SL. Dr. SHIMI SL holds a postdoctorate fellowship from University of Technology, Sweden. She has completed her bachelor's degree in electrical from Bharatidasan University, Trichy, completed her master's degree in power electronics and drives from Anna University, Chennai, and completed her PhD in electrical power electronics from PEC University of Technology. Now I welcome our resource person, Dr. SHIMI SL, for the session. Over to you, ma'am.
Thank you. Thanks for the introduction. And I think you can see my screen, is it?
Yeah, it's visible, ma'am.
Yeah. So like I couldn't see you people because I have made it. Yeah, now I can see you also. Like I put it in. A very good afternoon to one and all the students and all like other faculties who are sitting there. A very good afternoon to one and all. The topic which I'm going to cover today is a very close topic to mine. It is electric vehicle technology, and let us see some of the research scope in this. Though I'm not going to discuss much on the research what I did. It's a general what are the scope, what are the different research that can be done. So before moving into this topic, I would like to give my small introduction. I'm Dr. Shimi Sudhalata. I'm assistant professor here in the electrical engineering department at National Institute for Technical Teachers Training and Research, Chandigarh. So telling about the institute, there are 4 such national institute in India. One is in Chennai, one in Chandigarh, one in Bhopal and Kolkata. So all faculties, for those faculties, you can upgrade your skill and as well as knowledge by attending some of the courses at our end. So you can go through our O-Plan where you can see what are the different courses we offer. And telling about myself, basically I'm from Kerala, was born in Kerala, brought up in Tamil Nadu. My father was in DHL, so I was studying till my master's. I was there in Trichy. And after marriage, I had an opportunity to come to this north, the Chandigarh. And I did my PhD here from Punjab Engineering College, a deemed to be university, which is more than 100 years, like before independence. It was in Pakistan. And then after independence, they had shifted to Chandigarh. And at the same time, I got the opportunity to work here as assistant professor in this National Institute. And after my PhD, I got an opportunity to go to Sweden and work there under Professor Matt Bolan. So you can see him here. So he is a IEEE fellow. Like those who are working in the power quality area, you would have seen he has a lot of books in that area and a very well-known person. So I did my postdoctoral research at Lulu Technical University, Skellefteå campus, where this is the this is the power engineering group, all PhD and postdoc students here and faculty. So it's a very small group where they do only research and two extreme climates, you can say. So that was our main research I went to do there on electric vehicle in extreme -30, as well as on the normal climate. How does these vehicle behave and how much vehicles can be connected to the grid? And they wanted like power quality based research. So those are the research which I did there. And the group mainly works with, one second, this I can't. Okay, that doesn't go. So here, the group mainly works with power quality, low and medium voltage distribution, electricity market, transmission system reliability, and electromobility. And for those who are interested, every 6 months you can just go to the Luleå Technical University and search. Those who want to do masters after your bachelor's, there it is open. You can directly apply to the university. You can because they have some international student seats are also there. And for PhD, it's just like a job. You have to just apply if you're in this area, which I have shown here. So if you apply for PhD for 4 years, they will fully do scholarship also. And you can work there for PhD as a, there it is like a job. PhD is just like a job. And for postdoc also, those who are interested, for every 6 months, they advertise this and they have interviews and all those process. If you go through, then you can apply in this group because it's straightforward. There is no recommendation or anything. If they like you and your performance is good, you can go through. Okay, and the main work which I was doing is on the electromobility. I got the research fund from the Swedish Energy Agency, and first I did a pilot study on the impact of electric vehicle charging on the power grid. And after that, the main study was that done mainly, many small studies were done. One was the impact of temperature on the EV charging and measurements on coal car testing centers and fast voltage fluctuation and light flickers. Like when EV is charging, sometimes in the garages and other places, the lamps which are there, they flicker, though we can't see it as such. So what are the effect it causes on the human, as well as what type of power quality issues they create. So such studies were done. And I just had a workshop to disseminate my result and then publish papers. Then after this work in 2021, I returned back to Chandigarh, NITR, and now I'm here. My main area of research are power electronics and drives, digital control, artificial neural network, fuzzy logic, facts, renewable energy. Mainly, if somebody have attended my course, mainly it is on MATLAB or hardware with its interface with different softwares. So an optimization. Then now I have gone into electromobility, power quality, and big data analytics is some of the area which I'm working. And now I'm fortunate to get into PEC as associate professor. So mostly by next week, I'll be shifting to Punjab Engineering College, deemed to be university, as associate professor. So that was about myself. And today's topic, which we are going to see, is electric vehicles and some of its challenges, as well as we did a small prototyping here. Might be that gave me an opportunity to work in Sweden also, because we had done, it's just a prototype and studied about these electric vehicles. So first question which comes to the mind is, why do we want to go for electric vehicles when you have these internal combustion based cars and trucks, vehicles are there. What is the need to go for electric vehicle? Any of the student there, can you just answer? Why do you want to go for the electric vehicles? Any of the students, why do you want to go for electric vehicles?
To reduce pollution.
Yeah, that's good. So first point, yeah, everyone, as you say, it may be better like emission profile. But do you still feel that, yeah, like electric vehicle reduce these emissions? From where do these electric vehicles get their charging done? From the grid? So grid, again, the power is from mostly, like most portion, if you see, it's again from thermal. Is it? Thermal power plants. We are not fully shifted to renewable. So again, do you feel that we are reducing the emission by using EVs? Do you feel, students? You can keep it interactive. Okay, so here, if as somebody said, yeah, if you are fully charging it from solar and other means, let us say that, yeah, EV is a better thing, because as government wants to reduce this carbon emission. But as a common man, like many of us, we don't like always, our main aim will not be to reduce these carbon emissions. You can see here, electric vehicle, yes, it has a lesser carbon emission. But as an individual, if you want to get an electric vehicle at your home, will you go for it? And what will be the reason? Say you just leave this emission. Okay, emission, yes. But for reducing the emission, you will not get an electric vehicle at your home. I'm sure. I'm 100% sure to help the like environment to reduce the pollution in the environment. Might be very few people think of, because you know the initial cost of this electric vehicle is very high. The place, say if you have some 5 lakhs or 3 lakhs, you can go for a combustion vehicle. But here, minimum, I think for Nexon, if you want to go for a Nexon, it is Tata Nexon, it is around 15 lakhs. Basic, you should have 15 lakhs. So nobody, you are not going to spend that much and go for that and save the environment. So why do you go for this electric vehicle? As an individual, why do you want to go for electric vehicle? Anyone can answer?
To reduce the fuel cost.
Fuel cost, very good. Yeah, on like long time, if you see, the fuel cost is less. Then any other?
The maintenance cost is less.
Yeah, very good. The maintenance cost is also less. Any other answer?
It's a riding comfort.
Riding, why? The other vehicle also, if it is made comfortable, it is comfort only. Might be sound is less compared to the other vehicles. Sound will be
bit powerful. They have a driving pleasure.
Drive cycles, like it depend again on the engines. So, and how much kilowatt motor you're using here. Yeah, might be that also, but main. Now you know that Indian government has brought a policy like scrap policy. After 15 years, the vehicle have to be scrapped. All these internal combustion engine based vehicles have to be scrapped. But in electric vehicle, that scrapping policy is not there. You can use it. And if you see the battery life of an electric vehicle, can you say what is the battery life of an electric vehicle the company gives? Is if somebody, how many?
8 years.
8 years. They give replacement warranty also. They say for 8 years, this battery, nothing is going to happen for the battery. That is the thing. So they are given 8 years. It goes till 10 years also. So if for the maintenance, if you see an electric vehicle, you don't have other maintenance, as somebody had already answered. The main thing is only the battery has to be changed. That to 8 years, the company itself is giving like warranty, replacement warranty itself they are giving. They say that for 8 years, nothing is going to happen. Maybe 10 or 12 years, you may change the battery. And the main cost is there only in the battery when you're going for a change. But after this 12 years, within 2 years, if it is the other vehicle, so within 15 years, you have to scrap it, but the electric vehicle, only the battery need to be changed. You need not scrap it. So that's also a thing. Maybe the initial cost of the vehicle is high, but on a long run, if you see, the running cost, if you see, of an electric vehicle is less. Okay, so and at the same time, we are reducing the emission and we are bringing different other advantages are there. Utilities can in future use these electric vehicle as a mobile asset also. So now coming the like a small calculation, let us do and see. So general internal combustion engine, if you take, what will be the size of that like petrol tank? How much liters will you fill? Though many of you will be filling how much?
20 liters.
20, so maximum it goes till 30 liters tank is there. So let us take a 30-liter tank is there, and the approximate cost of the like petrol for 1 liter is
104 rupees.
104. Let us keep it as 100 rupees on an average. So this is for an internal combustion engine. If you want to fully fill the tank, it comes around 3,000 rupees. And on an average, 1 kilometer, like 1 liter gives how many kilometers?
15 to 16.
15 to 16.
Yes.
So let me keep it as a higher end. Let me say that there are vehicles
20.
which gives 20 kilometers. In 1 liter, it can go till 20 kilometers also.
Okay.
So it comes around, sorry, 20 kilometers it can give. So 20 into 30, so around 600 kilometers with this 3,000 rupees you can drive. So it comes around 5
rupees.
5 rupees. It comes around 5 rupees. Okay. This is in case of an internal combustion engine. Let us now take general electric vehicle. Okay, so for the electric vehicle, let me show you this is a data where it's a working paper where battery capacity needed for powering electric vehicles in India from 2020 to 2035. So let us just search for Nexon. So a general model, because this is a fast selling one, so I'm just checking that. You can see it is the battery capacity is 30.2 and it gives around 200. Here it is said to be giving some 200 kilometers with one full charge. So it is here 30.2 is the kilowatt hour. You can see the battery capacity. The battery capacity is this one. So based on that calculation, so there we saw it was 5 rupees. So in this case, again, let us take that it is 30.2 for 30. And like for charging this on an average, 30 kilowatt hour. So 1 unit is how much does it cost in
5 rupees average.
5 rupees. Yeah, on an average 5.
For home charging.
Yeah. So like say in Chandigarh also, if you take, it goes till 2 to 4. Maximum is 4. But in Punjab and other areas, if you see, say like in Haryana, it is 6 rupees, and in Punjab it is 8. Okay, so let me take the extreme case, like 8 rupees. Okay, so 8 rupees per unit. So 30 units, it is around 240 rupees. And this vehicle, if you see, the Nexon, the company says that around 314 kilometer on one full charge they are giving. But after reading many blogs and all, what I understood is, when it is coming down, like when it is going uphill, it gives only 114 kilometers. And when it is coming downhill, it gives around 240, and a normal road around 200. So that's what we saw there also. So here in case around 220, it gives. So here also, if I take 240, it gives, or around 220, it comes around 1.09 or something like this. Okay, so this is the cost electric vehicle on an average when you are fully charging the battery. So for 1 kilometer, there it goes till 5 to 10, because I have taken the extreme case, so that's why 5 came, but it goes till 10 also. So 5 to 10 rupees per kilometer. And when it comes to an electric vehicle, here also I've taken the extreme cases, 8 rupees and all. When as you people were telling, if it is 4, it comes from 50 paise to 1 rupee. So you can see the like the rate, like how much is like when you go for running cost, the running cost of electric vehicle is very less. So there is a possibility that you can go for it. So this is the Tata Nexon thing, like company gives claims around 312. The regenerative it gives 240, that is uphill, and uphill it is 144, and downhill is the regenerative 240, and normal it is 220. The battery power, yeah, it is 30.2 kilowatt, and per unit, like I just calculated 2.5 to 8, it may come till for 50 pies to 1 rupee. Okay, so now let us consider that you have a electric vehicle and the motor is 5 kilowatt motor. You are using a 5 kilowatt motor, and your requirement is on an average on one day you have to drive for some 5 hours. So how much power is required, like energy is required? It is 5 is 25. So I'm very sorry, I have cold, so that's the reason. 25 kilowatt hour is the total energy required. And if we consider that the battery is around 300 volt battery, so you have different cars with different battery ratings, it goes till 800 also. So on average, general car, if you take, it goes till 300 volts. So on that basis, if we take 25,000 divided by 300, so you require a battery for running for 5 hours a day, you require around 83.33 ampere hour battery. So in market available is 100 ampere hour battery. Okay, so you have a battery which is 100 ampere hour, or general, you can run a vehicle. So now for charging this, there are different possibility. You can go for slow charging or fast charging. So you have different charging stations also. For fast chargers, you go for DC charging. They are very fast. Shadi mode chargers are there. Or for slow charging at our home also you can charge with our 3.3 kilowatt charger. That is with 16 amps and a single phase 230. In case if I want to write it and show you. So if 3.3 kilowatt charger you can use. In that case it is, if you see, 230 volts and 16 amps charger. That is a general single phase charger what we use at our home. So now let us just take a case that in case if you are charging this battery 100 ampere hour battery at a rate of 1 amp, how many hours will it take for charging this battery fully? Or we say usually 1C. Sometimes you would have seen the charging when you're defining, you say 1C, 2C, you would have seen this C term some places. So now I have a 100 ampere hour battery and you're charging at a rate of 1 amps. So how many hours will it take to charge this battery fully? Based on that only, like say fast chargers and slow chargers we define. So 1 amp it is a very slow charger. So it is a 100 ampere hour battery. I am charging at a rate of 1 amps. So how many hours will it take to charge the battery fully? Anyone?
So you are charging the battery at the rate of how much ampere? 1 ampere?
1 amps, 1 amps.
1 amp, so 100 hours.
100 hours it will take. So that's a very, like you just think you have a 100 ampere battery and you're charging at 1 amp, it takes a long time to charge. So it is very difficult. So that's why here 3.3 kilowatt, around 16 amps if you take, you can just see it may take 8 to 10 hours to charge. So if you charge at, say if you're charging the battery at 100 amps, it can be charged in 1 hour. Okay, so that's the concept of this charger. You can go and charge, you can use a slow charger. So there is a 7.6 kilowatt charger is also there. Let us 7.6 kilowatt charger, let me take. In that is nothing but a 3-phase 440 volt and 16 amps only. If you go for higher amps in this place, instead of 16 amps, you go for 32 amps, it can be charged at a higher rate compared to the 16 amps. So mainly the hours of charging depends on this current rating, how much current, at what rate you are charging along with the voltage rating also. So here in this case, if it is taking 10 to 12 hours, it may take here only 8 hours. And in case if you are going for like 160 kilowatt or higher kilowatt chargers, like it's Chadimo chargers and all, it comes to 160 kilowatt or 350 kilowatt. So there you can charge within 10 minutes or 20 minutes. So in foreign countries, if you see, the chargers are fast chargers, mostly DC chargers, which can charge at a faster rate. Here you can see, if charger is charged at 1 amp rate, it takes 100 hours. If you're charging at 100 amps, it takes 1 hour to charge. So based on that only, you will be designing your charger also. So there are many countries, companies in India also, they are making their own chargers. You have different, it is not that fully you are charging at 100 amps. That is also then the thermal heating of the cables and all will happen. So you have some combination like CCCV charging, we say, which I'll be showing you later. We made a prototype, I said. So there we use CCCV charging. So for sometimes at a higher current rate and sometimes at a lower current rate, in a combination you do it. Okay, so similar to our mobile chargers, you have in our mobile, you can see around 3000 milliampere hour battery you have, cell phones, what we have. So if you're charging at 3 amps, the battery gets charged in 1 hour. Okay. Why EV? That's again the same thing. I'm just concluding it. EV battery requires replacement in 10 to 12 years, but petrol car has a validity of around 15 years. The running cost of electric vehicle is estimated to be around 1 lakh after 6 to 8 years. But the fuel car, in case of a fuel run car, it is 4.5 lakhs for the same period. So in the looking at a longer period, and similarly the maintenance cost is also less in case of EVs. Okay. I'm very sorry. So here, standard load profile of, and this is also area of research for electrical engineers, the standard load profile of an average household, if you see, this is for Sweden, but in India also, you can plot like this and see. So here you can see, this is for 12 months. Okay, so starting from January till December. So in Sweden, all the winter months, it is very cold, so they use a lot of heaters. Then in the summers, yeah, the power consumption is less. Again, it increases. But during a day, like one day fully, if you see, you can see here, during the night hours, less power. From 6 o'clock till this 11 or something, the power is increasing. Similarly, during the peak hours is during the night hours. 4 to 8. During this time, if you see, the power is peak. Okay, and a general tendency of electric vehicle, if you see as a human being, if I am going and charging, even our mobiles, you think, during the working hours you work, and once you reach home, your tendency will be to charge it because the battery would have gone down. Similarly, electric vehicle also, so you're going for your job or somewhere, you're running, and once you come back, our tendency will be, let us charge it. So there is a possibility that the electric vehicles getting charged again during the peak hours. So this is a very problematic thing. So there are research going on to, we say it as valley shifting, or the peak we have to shift it. So that peak can be shifted during the daytime you can charge, or many people, if you are not like this is charging at your office or other things, or during the late night hours also, you can charge, and you can try to flatten the curve of the demand. Okay, the demand curve can be flattened. This is one possibility. So for this case, what you can do is, you can just take data from these transformers and you can just see how is your profile in your area. And then you can predict it, because now electric vehicles have not come that much, but in future it will come. So under one transformer, you can just predict how many vehicles can come. So in that case, if the vehicles are charging at that time, like a particular peak hours, what is happening. So how to flatten the curve. So you can have tariffs making the people charge at the lower tariff. So such research are also possible in this case. Okay, and next, generally talking about an electric vehicle, if you see, you have V1G, that is unidirectional flow of power. That is, you're charging the vehicle from the grid. You have V2G, or you can say G2V also. People use it in two different ways. That is a bidirectional flow, charging the vehicle from the grid as well as giving power to the grid. Then you have V2H, that is again a bidirectional flow, vehicle to home. You have solar panels in your house and you charge your vehicle from that, and at the night time using batteries or the vehicle battery itself, you can give it back to the grid during the off-peak period. Okay, so coming to this vehicle, like this is a single unidirectional flow. So you can see here, so in this case, this is onboard charger. This is said to be level 1. This is level 1 charger, the one which we use in our house. It is slow charger, we say, or it is type 1. Type 2 chargers are mostly used in European countries also. If you see, mostly they go for this type 2 charger. They are a little faster. Okay, and for both of these two type of charger, it is onboard chargers because they are AC. Okay, the supply what you're giving here is AC. So you require a DC supply, so you require an onboard charger here. So inside the vehicle, there will be a charger which converts AC to DC. Then power factor correction circuit will be there, again DC to AC. It gives the required DC at the DC bus. And then you have DC to DC converters. Mostly here, 12 volt load, like the electronic load, you have the lights and other things in the car. Mostly it will be 12 volt, or some of the load even 24 volts. Based on that requirement, DC to DC unidirectional converter is there. Apart from that, you have a DC to DC bidirectional converter with battery pack. So this is the battery which runs the traction system as such. So you have a bidirectional battery and the power is given to it gets charged also. Whenever required, it gets charged. Okay, and when it is required, it gives power. So many scope is there in making this DC to DC converter, like designing this DC to DC converter, this unidirectional converter. So many research are going on. Because when you take about this batteries, many types of batteries are used, lithium ion or like nickel-based batteries are there, lead acid batteries are there. And you would have come about the power density as well as the energy density. So mainly nowadays, to have the combination of this power and energy density, you go for these battery packs with supercapacitors. The combination of battery pack and supercapacitor is used so that more power can be, like when you're going uphill, these supercapacitors can give this power, like during that period, more power can be given for the supercapacitors. And when battery is required for a longer run, the battery can be used. So such combinations are also possible. So for that, when you want to use supercapacitors and these batteries, what type of power electronics should be used? So that's a very important thing. What type of converter? So many research, even one of our student here is working on this, like when supercapacitor and battery combination comes, like how to, during regeneration, how to charge the supercapacitors and the extra power, how to charge the battery. So such power electronic combinations and all these studies are also going on. Again, here in this place, whether DC to AC converter is required or AC to DC converter is required, that's the question again. It depends on what type of motor you're using here. Your motor can be again different types. It may be DC motors, induction motors, switched reluctance motor, or permanent magnet synchronous machine. So again, a lot of research is going on in that area also. Mostly permanent magnet, DC, like PMDC, that is permanent magnet DC motors are most commonly used in foreign countries also. But in Indian scenario, if you see, their permanent magnets are required and we are dependent on China and many other countries for these permanent magnet. So when we go for that, what happens? Our electric vehicle cost mainly depends on these there is the import, we'll depend on them. So that's why now a lot of research in India also is trying to develop these motors like polyphase motors or induction motor also. They are coming out with new concepts such that it gives a characteristic similar to these permanent magnet DC machines. So in that case, what will happen is we need not depend on other countries, and our car, the price will not depend on the other countries. So a lot of research is going on in this area of electric motor. Which type of motor can replace these permanent magnet DC machines, which can give a characteristic similar to that. Okay, so for that mainly the people use finite element analysis, like you have so that where like and Altair is another software which is having the same capability. So you can come out with new motors also, which has a characteristics of similar other DC motors, which can replace in this drives. Okay, so this is about the V1G. And next we go to V2G. In V2G, vehicle to grid, if you see, it's the same thing. Here now, from the grid, we are charging the battery. And now from the battery, you have to give power to the grid. So like say, you can give, but sometimes say during the daytime itself, you are in some parking lot. And if your vehicle is having a solar panel at the top, or your place where you have parked the car is having a solar panel, in that place, in that circumstance, what you can do is this solar power can, this solar can give power, charge the battery, and at the same time, it can give back power to the grid also. So such possibilities, bidirectional possibilities are there, and it is in working condition also. You can say that it is implemented in many countries, mostly the Nissan Leaf. From 2000 itself, if you see, the Nissan Leaf is having this capability, and the Nissan Leaf, in many places, they have implemented this also. So I'll be just showing you some case study on that also. अभी क्लास में है तो हाँ रख देना हाँ वहाँ ही रख देना. Okay, so this is the thing. Here, vehicle to house and house to vehicle. This is a concept. You have a house where you have solar panels connected. So accordingly, you can charge the vehicle, and during the off-peak hours, you can even give power from the battery to the house. Okay, so this concept is mainly in Nissan Leaf. In India, I think it will be coming after some 10 years only. This Nissan Leaf, it is not there in India, but in many other countries, in foreign countries, if you go, you can see this is a very common car which is used. So in Nissan Leaf also, same concept, like you can charge it from the grid or you can give power to the grid. And when solar power is there, you charge the car from solar power. And during the evening hours, that too, like when solar power is not there, then in that place, when an event is disrupting and the production of solar energy, the Nissan Leaf can help even out peak load and stabilize the frequency to maintain the grid stability. So it can give supply back to the grid. So what can be done is during the peak hours, it can charge, and during the it can give power to the grid. And during the off-peak hours, as I told you, in the late nights when the tariff is very less, it can get charged from the grid itself. So during peak hours, when the power is more, when the cost of the power is more, these Nissan Leaf or like any electric vehicle can give power. So you can start earning also. So that's also a concept. And it is not like what I'm telling you, you can earn from us. It is not a thing that doesn't happen. Actually, if you see, this is in UK. Like you can see here, in UK, there is a project where the drivers, when they have parked their vehicle in the parking lot, they earn around $1,200 per month by just standing in the parking lot. They earn by using these Nissan Leaf. So this is a model. And similarly, during the 2011, when there was a nuclear disaster in Japan, to stabilize the grid, they had used these Nissan Leaf. Okay, so during the Tokyo earthquake and Faxi, many times Japan had used these electric vehicles, the Nissan Leaf, for stabilizing their grid. So even in Virginia also, the experiment is going on. So in future, this is the thing. We are just going to use these electric vehicles as a moving battery, you can say, or a moving source. Okay, and wherever you want to stabilize the grid. And this will be the future. That even when you take your vehicle, come to the office and park, and if you feel like there will be apps, and app will ask you like, are you ready to sell your power? So in case if I am ready, you just plug in and you can give power to the grid when the tariff is high. And when the tariff goes low, like evening hours, or you feel that, okay, now like the power cost is less, you can charge your vehicle also. So such things are going to happen in future. So for that, the software development, this like the security of the grid, and all these things, many research are possible in that area also. So mainly when you talk about these electric vehicles, electric machine, there are DC machine, that is DC motors used, DC series motor, then induction machine, permanent magnet synchronous machines, reluctance, switch reluctance motor, and synchronous machine. So these are the different motors, and these are the different batteries that can be used. So here the battery that includes sodium is written as Na, such as sodium chloride, sodium sulfurs are used for this purpose. Nickel-based batteries are also there, nickel ion alkaline, nickel metal hydride, nickel cadmium. Lithium-ion batteries, as we all know nowadays, mostly lithium-ion batteries are used. So talking about the trend, if you see, DC machines are used from late 1900. If you see, DC motors were most prominently used. But after 2000, you can see there is a very great increase in permanent magnet synchronous machine. But nowadays, this green line also you can see, induction machine, lot of research in Indian, according to the Indian scenario, lot of research is going on in this induction motor also. So this is about the market strategies. Coming to the storage technology, as I already told you, there are two keywords. One is said to be the power density, and another one is said to be the energy density. So you can just keep this in mind, a very important concept. So you know that for when your car is want to climb the hill, so during that instant, like when it wants to go uphill, the thing required is the power density. Okay, when it wants to go uphill, climb anything, it requires power density. And when we were there, like how many number of people are sitting inside this car, or how long it has to go, that depends on the energy density. So you won't require both. You want big combination of this. So you can have a combination of fuel. Okay, so many research can be done in this combination using hydrogen. Okay, hydrogen-based fuel cells and capacitor. So that when you want to go like during the starting also, say you're in a like a signal and you're going to start it, or when you want to climb the thing. So during these position or during those time, you require power density. And the other thing is like how many people you are going to, how far you are going, or how many passengers you are carrying, it requires the energy density. So a combination of this battery is also having a high energy density, but it is less than fuel cell, but still okay. So nowadays, in this scenario, if you see in India, we are going for battery as well as supercapacitors. But the future is we will go for fuel cell as well as supercapacitors. So if you want more research to be done, you can just explore this area. Okay, so that's one thing. So nowadays, yeah, this coming to the battery, as we all know, nowadays the lithium-ion battery or the combination with lithium with different polymers, that combination is trending. Okay, because of its own characteristics. So some of the area where these research challenges are there is large battery weights, load, long charging time, high initial cost, battery life, billing, carbon credits, data management, security, privacy, consumer acceptance. So these are the, like, as a consumer, we should also accept it because the initial cost is high. We don't go for. So these are some of the challenges which we have. Being electrical engineers on the electrical side, if you see, overloading of power equipments and therefore the transformer and all these cables and all those things. So like in Sweden and all, when we were doing, there were people who were coming that the cable failure has occurred in the joints. So what might be the reason? They are studying the different reasons why it is happening. Okay, so there are, like, now it is time to study on these power quality also, power quality side, grid power quality issues due to EV penetration, because EV is a power electronic based device, you can say it's a non-linear one. And these power electronic devices, they switch at very high switching frequency. So when these power electronic frequencies, if you see, like it may go from 2 kilohertz till 150 kilohertz also. So from 2 kilohertz to 150 kilohertz, we say it as supra harmonics, and they propagate through the grid. And many a times, even the solar, when it is solar plant is there, they also have power electronics there. So the supra harmonics, they travel through this grid and can be seen far away places. But in electric vehicle, if you see, so your house is there and it's a distributed generation. You just think you have solar, you have EV charging there. You have a power electronic based circuit, in the sense you have an electric vehicle. Your neighbor is also having an electric vehicle. Might be the harmonics, that is the supra harmonics from your house, may propagate through the cables, that is the impedance, like you can say the cables have impedance. So it is propagating. It may go to your neighbor's house and may trip the the ECB, like the RCD, you can say that it may trip your RCD there. Okay, unnecessary tripping of RCD, or sometimes these harmonics can cause flickering of light. So these things can happen. So many power quality issues, since it has, like in Sweden and all, many vehicles are charging. People are coming with complaints saying that we have this light flickering when we are charging, or some humming sounds are coming. So many research on this power quality side is also going on. Large number of fast charging EVs could introduce serious voltage distortion and instability problems. So that's also a problem in the thing. So this I'm skipping it little. I'm making it little faster because I think we'll go short. So some of the standards and regulations which are there. Just let me just see the time. Yeah, we have around 15 minutes. So role and functions of various agencies, if you see, that is Central Electricity Regulation Commission, which defines all the regulatory frameworks included. Then you have the standards, connectivity, safety, and products. So Bureau of Indian Standard looks into these equipment standards for the equipments, and Central Electricity Authority is also there for standardization of these load factor, power factor, and all these things. So you have this IEEE. IEEE is energy storage, and the IS smart building, load, and customer. These are the IEEE based societies which are working on the standardization of these different standards which is required for electric vehicle. And a very important standard you can see is this for the electric vehicle plug standards, for charging plug standards. That is, one of is IES 62196, which is type 2 chargers mainly use this standard. Okay, and similarly, the Society of Automotive Engineers, J2954 standard. So that also power quality only, how much third harmonic can be injected into the grid, how much fifth harmonic. So all those standards, like we all know, it also follows the this J2954 also follows IEEE 519 standard only. Like 5% is permissible in the grid. But apart from that also, they have many other parameters defined here. So if you are going for a charger construction or something, you have to follow all these things. You have come out with a new charger. Then before putting it in the market, you have to test all these things, like how much third harmonics it is injecting into the grid, how much fifth harmonic, and is all these harmonics within these standards. So that's a very important thing. And there is an IEEE IoT consortium that is working on the IoT side of these electric vehicles. So they also have standards. So we have to look into these standards while we are doing our research. Then we have this in India. If you see, there are two main organizations. One is ARAI, that is Automotive Research Association of India. Similarly, ICAT is there, that is an International Center for Automotive Technology. So these two centers, whenever you come out with a new product or you have come out with new thing for your electric vehicle, the testing and all those things you do at these two places. ARAI is in Pune and this ICAT is in Delhi. Okay, so in Delhi, if you see, they have very even extreme -40 climate condition. You want to test your equipments, it is there. They test all those things there. So these are the two main, and they have some rules and regulation that you have a charger. It should be a separate transformer should be there. What should be the cables and other transformers ratings and all these things they define. And they have said that whenever a charging station is there at some place, a network service provider should also be connected with them, because in future, like online booking of slots and all these things we will be doing. And mainly in Indian scenario, if you see the chargers, one is Bharat AC, that is a 10 kilowatt charger. Bharat DC is there, it's a 15 kilowatt charger. Okay, and then type charger. This is a charger like in Europe and all, very commonly, even in Indian scenario, type 2 this charger is available. So this is a three-phase charger only where you have this R. This is for the R phase, Y and B phase, and a neutral. And then you have these communication ports also along with it. Okay, and this DC charger also, these are the two ports. Apart from that, others are the communication ports. Sadimo charger, it's a Japanese charger. Sadimo means like type have your tea. Okay, so they are saying within the time you have your tea, it gets charged. So that's why I said this is Sadimo chargers. It goes till to 350 kilowatt also. So 350 kilowatt, within 5 minutes you can charge. So this is a DC charger. Similarly, one more type of charger is this CCS charger, that is the combined charging system. So there you have DC as well as AC. So that combination is available. So this is the AC charger. The AC maybe this is a single phase charger along with its communication port. Or there is three-phase also. Here there are RYB with the communication. So that is also possible. And along with that, they have the DC also. So this in Indian scenario also, many places, the CCS chargers are also used. And other thing is, this was a plug socket standard, which I was telling, IEC 60309. Can keep this in mind. So according to that, the maximum allowable voltage is 1000 volts, DC or AC, and the current is 800 amps, and the frequency is 500 hertz, and the temperature is -25 to 40 degrees. And when we go for charging also, if you just look into the charging port, sometimes it may be white color, sometimes orange, sometimes red or black. So it is not like they like it and they have put it. It is based on these standards. They have that if it is a DC charger greater than 50 volts, it should be white color. If it is 500 to 1000 volt charger, okay, for marine, usually it is for marine vessels and all, they use the high voltage. So it will be black color. If it is a general 300 to 480 volts AC, three-phase, it will be red color. So hereafter, when you go, just look into the charger, see the color, and based on that, you can identify that what is the rating of the charger and all those things. And as this I already told you, in DC charging in India, if you have this 48 volt and 72 volt chargers, there is 10 kilowatt or 15 kilowatt. So that is level 1. And if you go till 30 and 150 kilowatt, it is level 2 DC chargers. And there are many like charging slots, you can say, Sadimo type or CCS type. Superchargers are used for Tesla and GB Bharti. So that's also used for some of the Mahindra vehicles and Chinese vehicles. So these are all the different charging socket types. Okay, so this is the CHAdeMO type. You have this is a DC one, CCS. It has AC as well as DC. GB-T is a DC charger. Okay, AC chargers, if you see, again, in Indian scenario, 2.5 kilowatt to 3 kilowatt. That's generally one which we use in our houses. It goes till 8 hours and 10 hours of charging. Fast charging is also there, AC till 22 kilowatt. Okay, so this is also some of the chargers. This is the type 2 charger which I said, 621906, a very common charger which is used. So a general thing for understanding I have taken like this. Single phase 3.3, this is what we use in our houses when you're charging. It may go till 5 to 6 or even high, based on the CCCV technique what they have used. It may even go till 10 hours also. 7.4 kilowatt charger if you take, the current rating is high. When I told 16 amps, that's wrong, it's 32 amps. So 2 to 2.5 hours charging. If you go for a 3-phase 11 kilowatt, it is 16 amps and it is 1.5 to 2 hours charging. Similarly, 432, that is 40 minutes, and 63 amps. When a higher amps, the minutes gets lesser. And mostly these are the CHAdeMO type chargers, where 50 kilowatt DC, it takes 20 minutes, and 120 kilowatt with 350 amps, it takes around 5 to 10 minutes. Okay, these are some of the companies which are doing it. So this was a small project which we did here in NITR with our master students. We made a charger, like an electric vehicle charger, which can charge from the grid as well as from a solar. So in that case, we used here a solar panel, a small one. It was only a prototype. We use sensors, current and voltage sensor, all effect based sensors, and microcontrollers were used here. And like it can be interfaced with PC also. Like if you want to implement some algorithm like MPPT or something, that was simply for research purpose. They implemented that also. A DC to DC converter and a battery is there. So you can charge it from solar. But when there is no solar power, at that time, you have your AC, your rectification, then DC to DC conversion, and this is a relay, DP/DT relay. So at that time, when solar power is not there, automatically the signal will change this to the other port, this one. Okay, so automatically from the grid, the power is got. So this is the thing. For this, MPPT was used. So in this MPPT, the logic is you take the voltage and current, you measure the voltage and current at one instant. And again, you just perturb the system. That is a DC to DC converter. You give a duty cycle and you perturb it. And again, you see what is the voltage and current. It may be V1 and I1. So we see whether there's voltage and current is, that is the power is increasing or is it is decreasing. Based on that, again, you change the duty cycle in such a way that we have to bring this point, that is we want to make the solar panel work at this point. So that is actually the MPPT. I'm not going much into it. Such an algorithm was used. First of all, we tested with MATLAB. The students had done that. After this, we tested in hardware also. So I'll be showing you that. So this is with MPPT and without MPPT. So when we used MPPT, more power was tracked. So for the battery, this was a prototype, as I already told you. We took it from our computer laptop only. So 4.2 volts, 6 lithium ion bat cells were used. So 6 was a 24 volt was made. And in that case, first what we did is we did CC charging, and then after that CD. So CC like is constant current charging, and I already told you. So for example, we have a 20 Ah battery, and as we said, if it charges at 1 C, it takes 20 hours. If it charges 20 C, that is 20 amps, it charges in 1 amps. The same concept here. First, we charge with 0.1 because it's a prototype, as I already told you. 0.1 C, so that is 0.1 amps. Till the voltage reached 17 volt. Once that volt was reached, then we charged at 0.5 C until it reached 24 volts. And after that, slightly we kept little above then we shifted to CV voltage, that is constant voltage charging, so that the voltage remains constant. The CC was shifted to CV and it was voltage was kept constant, and a trickle charging was done so that the voltage don't go down. Okay, so though 24, we just kept little higher so that the voltage is maintained. For this, the circuit student use it was this one. So here you can see here, this is the solar point. Okay, and like solar panel is there, and there is a DC to DC, sorry, this is a DC to DC converter, a boost converter connected to the relay. So when solar power is there, the boost will boost the thing and it goes to the relay, and the battery has to be charged. So you can see the battery points here and here, and the relay is operated, and first 0.1 CC charging was used. So this is a constant current charger circuit. So this get activated. Okay, and first until 17 volts. After 17 volts, this pot gets to the other mode. So it goes to 0.5 C. Once it reaches 24 volts, then this circuit gets shifted to the constant voltage circuit. So now the battery will start charging with constant voltage. Okay, in case the solar is not working, there is no solar power or it is night time. During that time, from grid, the supply is taken. This was a boost converter, and the relay will operate. And from this grid, the power starts flowing to the like battery through the CC and CV charging techniques. So this was a logic which was developed. And to see the state of charge, we use this LM3914IC. That actually for seeing the state of charge, there are different other techniques. This is a very poor technique. But since it was a prototyping and students were doing, just want the voltage base, how much it is, what is the voltage, based on that, we say how much the battery has charged. So based on that, this technique was used for voltage technique was used. And we used a DC motor, and we just with solar panel also we were trying to charge it. So and during the grid time also, this is solar. So when solar panel, we just close the solar panel, it shifted to grid and it starts charging. And discharging we did with this motor arrangement. So this was a basic thing. After this, what we did, we took this and we when this student did it, he found a lot of current ripple in that DC to DC converter, the boost converter which he used. So after that, what we did is, this was a boost converter. This boost converter we removed, and another student for next 6 months, that was first it was done by Arshdeep, and after that Renu was there. So she modified this interleave, like the solar and same circuit, but she interleaved a boost converter she put here. So with an interleave boost converter, the voltage rating was also uplifted, or you can say it depends. And that was a new topology. She tried to improve that topology also. And with like based on how many DCMs you're connecting here, this combination, your voltage level also V0 by Vn is equal to this. So the voltage level was also boosted up. And here the current ripple was also reduced. The charging current ripple was also reduced in this case. And this was a modified IBC coupled inductors which we made. And after this, this was implemented in a small prototyping car. We just tried to implement it, and the student started driving, sitting on that. They drove also, and they checked everything. Okay, and the ripple was also reduced. The same circuit, then what we did, we tried to implement it in a vehicle which was made by our students itself. That was again the next batch students. And the mechanical engineering students, they designed this such that it can have high payload. Like it was used for in our institute itself, inside the click, it can carry around 170 kg of load. So for load shifting and all, they use this vehicle. And it was lead acid based only. We did it because cost effective. We didn't go for lithium ion battery, but now more research is going on in this also. So here again, the same circuit which I showed you. With that, we started charging this battery with solar as well as grid also. So such a lecture is there in YouTube. I had given all the technical details. So this was the extension of that work. After that, this was a research which I did in Sweden. like seeing all these things only, I got an opportunity. So when I worked in EV, they were also interested, and there it was a different type of research where they have already fast chargers connected in many places, and they are fully most of the vehicles electric vehicle. They have shifted to electric vehicle or hybrid vehicles. Okay, and what we did is we went to a testing center, electric vehicle testing center, and we connected a power quality analyzer in the PCC, that is the point of common coupling. And there are many electric, there are around 8 fast chargers where there are 4 of ABB and 4 of Fuji. And there we put the power quality analyzer, we took the data, and we try to analyze the data that what are the problems, the power electronics, because they are all new vehicles which are not in the market. Okay, so they are brought into a place called Ting Tong. In that Ting Tong, they connect, they run the vehicle in all extreme -30 with full snow condition, all extreme testing they do, and then they come and charge there. So our job was to find out that the new type of power electronics, what they have put, what type of problems they have, what type of harmonics they are creating, what other problems they can create to the grid and all those things. So some of the limitations, I'm not going, I think we are short of time. So there are a lot of problems these electric vehicles can bring, like the under voltage problem, over voltage, unbalanced. You have an RYB phase, and you know that, say, one particular house, they are charging under one phase, and the other phase, other house under another phase. And under the transformer, if you see, it is not known like who's going to charge when. And if you see the same phase, all the houses have connected their EV in the same phase, there may be unbalance there or under voltage. And now the combination of solar and EV is also there. So whenever a solar is connected, it tries to, it's the load there. So it tries to reduce the voltage at that end. But when it is a generating like a solar, whenever EV is connected, it tries to reduce the voltage. But when it is a solar, it's a generating thing. So it tries to keep the voltage of that phase little higher. So this also may cause, the solar EV combination may also cause a lot of problem. So a lot of research is like possible in that area also. So it's almost 1:05. Like just I take 2-3 more minutes and just show you some results of what I have done. So this is an ABB charger, which I said like 160 kilowatt or 350 kilowatt. The same charger can be made with both the kilowatts. It depends on the power electronics. So 2 such power converters are kept. It can go till 350. The measurement which we did was for 160 kilowatt, 375 amps. So this was for 1 month fully we connected in one particular charger. There were 8, but one we connected. And these are the charging cycles. This is different electric vehicles coming and connecting it. So one enlarged version of 6 and 7, 1 day is shown here. And you can see here that this is one electric vehicle, which is charging at like around 75 amps, it is taking and charging. You can see another vehicle, it has taken around 200 amps initially, then it has gone down. So yeah, you understand that CCCV charging techniques I was showing. So they have used different combinations, and that's why this different patterns. So different vehicles have different patterns. Some vehicles, they charge very fast, like this is within 20 minutes or 10 minutes it has charged. Some takes 1.5 hours or 2 hours to fully charge. So it again depends on the battery capacity and the type of charging technology they have. So these are 2 different vehicles. One vehicle charging at 50 kilowatt, another vehicle charging at 11 kilowatt. Okay, so this 11 kilowatt, it has taken around 1.5 hours to charge, a longer time. But this within 20 minutes, this electric vehicle has charged. Okay. And one more thing is I was telling you, the supra harmonics I was telling. So these are the harmonics between 2 kilowatts to 150 kilowatt. Actually, short of time, I am just putting everything together. This was a measurement we did in our laboratory. One of the person, he came and complained that whenever he is charging his electric vehicle, the lamp in his garage is flickering. So just to study that, here supra harmonics was taken, like it was studied, his vehicle was connected, and the PCC at the electric vehicle end and at the neutral and protective earth, the readings were taken, and we could see that this was the electric vehicle charging frequency. Okay, it was around 6 kilohertz frequency. So 6 kilohertz, it's said to be a supra harmonic, and we could find that the 6 kilohertz component was there in the PCC also, and even in the protective and neutral and protective earth. So this neutral and protective earth, if it is there, it may cause RCD tripping, and at PCC, it may go into the grid also. And this was a study which was done for light flicker. So this super harmonic component, which I am saying, they did a study where this is an LED. Okay, taking an LED lamp, say an LED if you see from a single phase supply, and then there will be a rectifier, diode based rectifier. Okay, so here a bridge rectifier, you think I'm just drawing one diode and showing you. After that, there will be a DC to DC converter. And then at the end, these LEDs are connected. Okay, the light emitting diodes are connected here. It will be a string. Okay, so lack of time, I'm just showing you as dotted, like lot of LEDs are connected here. So what happens is, when an electric vehicle is, say, connected to this point, and a lamp is LED is also connected to that. So here there is, let us imagine that there is a electric vehicle connected. And what happens is, I told you about the supraharmonic component. It may pass through this. And this supraharmonic component, when it passes through this diode, the conduction period of the diode changes based on the magnitude of the supraharmonic component. So what happens when the diode conduction period changes, the current flowing through the LED also changes. So that's the reason that light flicker was seen. The light was dimming, that is because of this. So such a study was done. Here what they did, they took supraharmonics of 3 volts and similarly 7 volts. So this was for the 3 volt and this was for the 7 volt. So when 3 volt was given, actually the conduction of diode should be like this. This is the conduction period. But what happened? The permanent conduction is only till this. Because of this supraharmonics, this red color component superimposed on this, it can be seen that there is a less conducting period here. Here you can see that less more the conducting. This is said to be intermittent conductance. So the group found that this is Selchuk, one of our PhD student had did along with Matt Bolan. So he had found that when the supraharmonic magnitude is increasing, the intermittent conduction period is also increasing. So based on that, the diode conduction time in this case is only here.
Ma'am, I'm interrupting, ma'am.
Yeah.
Ma'am, the Zoom meeting is scheduled till 1:15.
Okay.
It may get connected.
Okay. So this is the thing. With this, I am just finishing it off. Actually, the LEDs, LED lamps, conduction period will change because of the diode. So because of this also, light flicker. So similarly, many other research based on the sound also, when they are charging, they create some, like the supraharmonic component creates some humming sound. So many research are going on in that area also. So these are some of the research, and this future, what are the LiDAR is there, inductive charging systems are there, in-hub motors within the wheel, and these nitride inverters, which can operate at high voltage, high temperature, high switching frequencies. Then power electronic base, compound semiconductors are nowadays used. You can see like gallium and other things are also used for this. And lithium ion batteries and ultra capacitors, carbon polymer composites used for reducing the weight of solar panels, and processors, many rolling. This car can be said as a rolling supercomputers, and some lightweight metal chases. So I'm just giving you some insight. So with this, I come to the end of this lecture. Okay, I took a little longer because these the individual topic, it takes a long time. I try to cut short it, that's why. If you have any doubts, you can ask. And I think might be you have got some insight on this topic. So thanks for Rini and all these people who are sitting here and patiently listening to me. And if you have any doubts or anything, you can just ask me.
Thank you, ma'am, for this valuable session. Now I request Levin Sabi of S6EE to deliver the vote of thanks.
Good afternoon, one and all present here. It gives me immense pleasure to deliver this vote of thanks for this event to all the dignitaries and the students assembled here. First, I would like to thank our resource person, Dr. Shimi SL, for giving us precious time in her busy schedule for this wonderful section. I would like to thank our beloved HOD, Mrs. Lena Thomas, staff members and students for making this function a grand success. Once again, I thank each and everyone present here at this event. Thank you all.
Thank you, Levin. Thank you all once again. Now this technical session has been dispersed.
Okay, thank you. Thanks once again for calling me. And with this, yeah, we come to the end of the session. Thank you.
Thank you, ma'am.